So today we're gonna do two things. We're gonna first finish up some of the tutorial from last time. So we're gonna keep finishing up that walkthrough. In particular, we're gonna talk mainly about images, which we didn't consider at all before. And then we'll secondly talk about putting it all together and how you actually deploy the system on, not just the ones that we know about, but the items that we don't know about, because there aren't many reviews, right? So how do we apply it to then, deploy this thing and figure out what are the best toys that aren't very well known yet coming through the pipeline. After that, we're going to spend the majority, well, probably may end up being half the class or so, talking about data science positions. So I imagine that the reason a lot of people are in this course is that you are interested, at least in the possibility of a data science position or using data science in your position. And I'll talk about that a little bit, and we'll go through some of my take on what the data scientist market actually is, what that means, and sort of how you can go about getting a data science position if you so desire. I have a cold today, so apologies if you can't really understand me very well. I'll try to, if you need me to repeat anything, just let me know. Usually I can hold it off until the end of the semester, but this time I wasn't quite able to do that, so apologies for being a little bit gravelly in my voice. Okay, so when we finished last time, we had done two things. We had basically built a machine learning classifier to differentiate between the worst toys and the best toys. And this is a little bit odd because in reality we're going to still apply it to the entire set of toys. But this gives us some notion of a classification task we might have some chance in succeeding at. We ran a few diagnostics to figure out what sort of classifiers worked best. Why is that doing that? Something's wrong with that projector. It was doing this before, too. It looks like it should be displaying here. Let's see. I think this is maybe a connection up there somewhere. So we'll just focus on this one. For example, we looked at the performance of the different methods with different amounts of data. So varying our sample size from a very small sample size to relatively large. We looked at different classifiers like boosted decision trees and logistic regression. In this case, actually, kind of unusually, maybe logistic regression performed the best out of these things. So we're going to go with that. That's not a common occurrence, but for whatever reason, in this data, maybe that decision, that hypothesis function of just linear functions in the data ends up being a good one. So that's the one that it picked here, or that's the one that we picked here. And then probably and actually one of the benefits, though, I have to say about logistic regression or any linear model is that we can inspect the classifier results now. So the next thing we did is we actually, remember, logistic regression just is a linear hypothesis class where each term adds a weight towards positive or negative, and you apply the logistic function to determine what class it is. And what we found were the weights. These were the weights. So toy, the word toy, makes it more likely to be a bad toy, because if it's a toy, you'll need to say it's a toy, I guess. Bath makes it more, or water, I guess, makes it more likely to be negative. Also, bath makes it more likely to be a bad toy. Whereas a lot of the things like brand names that are known to be good brands, like Melissa and Doug, green, where's green toys next. These are all kind of bump up the probability of being positive. I don't know why toys is positive and toy is negative. Maybe you might as well get more than one toy if you have a toy, right? If you're going to take it. So some of them are a little bit opaque, certainly, and don't expect to understand everything it does. If you did, then you wouldn't need to do any machine learning. But for the most part, these actually are pretty understandable, right? Some sort of good brands kind of bubble up to the top. Some looks like ultimately bad brands, or bath toys. It seems like are really bad according to this thing, right? So a bath toy is like the worst thing you could ever have. Yeah, without a brand name, it's a bath toy. That would be an awful rated toy. So this is great. So this is sort of a first pass, but at the same time, it's pretty. It seems pretty kind of naive here, right? At the same time, so maybe we want to add more advanced features into here. So one thing I did is exactly what we talked about. So I guess prefacing this, when we downloaded the data, we downloaded both the name of the toy as well. I mean, it's kind of a long name, but we downloaded the name as well as the image that toy had. So the next thing I did was using the exact same code from your homework, so I can't actually show you this code. I took all those images, I placed them into the VGG pipeline, and I extracted the last layer of features from that. I actually even went through some of the dense layers too. not just the convolutional layers, but I also resized it to be the same size as the ImageNet pictures, and then took the very last layer before the final softmax that VGG uses for ImageNet. I used that last layer of 4,096 features. Man, my voice is getting worse, I feel like, as I go on here. So hopefully I make it through this lecture. OK, and so let's talk about now images. So image features. So what I did was I saved it all. I went through the whole pipeline of basically creating a matrix for all my training set where the image feature is generated from VGG. We're just saved as a matrix, the same size as my original matrix. And I kind of went through all that. I'm not going to show that here. Hopefully it lines up with exactly with the ones that I output, or I'll have results that I will tell you are wrong. But x image equals load f. OK. And let's, at the end, I think we created our training set from this matrix x. So I'm just going to, for now, use x as all my images instead of anything I had before. So I'm going to ignore the price. I'm going to ignore the names. I'm just going to use the images now. And we'll see how that does. Oftentimes, when you want to consider a new feature, it helps to consider that feature in isolation. So you might want to say, is there anything this feature tells us that can offer any benefit? And this is a good way of kind of testing that. Though I'll get to a second, the more important question, which is, can this add anything to our actual existing classification? So here are our images. I'm going to go and I'm going to split our test set again into a test set and train set. And I'm going to build a logistic regression classifier on this. A logistic regression. I think I use let's not use C as equal to anything yet. Before we do that, let's go through this exercise of plotting a pretty wide range of regularization parameters to see if we can do well at all here. Yeah.
About you said considering the feature of isolation. Actually, theoretically, it could happen that one feature on its own does not tell anything, and the second one does not tell anything, but together they're a lot.
Yeah.
So how it happens in practice? Like, is it rare? Or?
So the fact that one feature by itself is not valuable, other by itself is not valuable, and somehow their combination is this super valuable feature. Two comments about that. First of all, in a linear model, this can't happen, because linear models are always additive. So if a feature is beneficial in a linear model and by itself, it will be beneficial with something else. Now, it is absolutely the case that you can have these XOR functions, right, or something like that, where if you have only, you can easily come up with a case where when you have nonlinear classifiers where that is the case, where you have two features that only together mean anything, but that separately, a nonlinear function of them together means something. A linear function of them separately means nothing. It is, though, in practice, unusual. You sometimes will see additional performance that sort of goes above what they're both together, even the marginal contributions of each one. But you're unlikely to see zero correlation on each of them independently, and then some magically you get this perfect correlation between the combination. So possible, but unlikely. OK, let's go back to get this is my range I'm going to have here. I'm going to run a bunch of different logistic regression classifiers. And I'm actually going to pick a bigger range here. I happen to know that you need a bigger range for your allowable C parameters, but don't worry about that. You will just, in practice, you would just test it once and see what happened, and then it wouldn't do what you wanted it to do, so you'd make them bigger. OK, let's see if now we've had the moment of truth, whether my images here lined up with what I generated previously in my own text. All right. So here's our data. So here is the training error in blue. Right. So that does what we expect when you have very low regularization. Very low C, being very high regularization. C again is the inverse of lambda as we've used it. You get essentially the performance of a zero classifier. It's a little odd. It's actually slightly better for there and slightly better chance by just randomness here. This is slightly better than chance, actually, because no matter how low you make it, you always get some little effect. So this is slightly bigger than 50-50, but it's still pretty low. And then you climb up to 100% accuracy in the training set very quickly, because these are a lot of features, right? There are 4,000 features here. Actually, I should have shown that. We have 2,800 examples. We have 4,000 features here. Of course, we actually much fewer than that because we're sub-selecting. So we actually only use however many we use. Saw before. We use 260 or so for training, 275 maybe. But very quickly, we're able to get 100% training error. The test error does something a little bit not quite as nice. It kind of bumps up, and this is actually a little bit above 60 there. In fact, let's see what it is. So that's around the level of C being 10 to the negative 4. So let's just see what happens if we actually build logistic regression with C equals 10 to the negative 4. C equals 1, E negative 4. Fed X, Y train, and let's, I don't know what that was. And let's see how it works on, well, first of all, see how it works on the training set. And secondly, let's see how it works on the test sets. Cross validation. Okay, so we're like at 61 or so, maybe a little bit. This is around a little bit higher than 60. So that actually is better, in fact, than random guessing. So this sounds good, right? I mean, somehow these features are telling us something about our data that we didn't really know beforehand. So this seems good, and it's actually kind of impressive in some way that, you know, just looking at the image of a toy, you're able to tell, you know, at least on this cross-validation set, but I'd wager this. We can see what it is on the test set too. Maybe I'm going to be. I don't think I haven't tried this actually, so we'll see if I prove myself wrong here. Yeah, not bad, right? So definitely better than random chance in terms of just guessing what's going to be what's going to be a good toy and what's going to be a really bad toy. So that's great, and that actually is like I say, fairly impressive given the difficulty in processing images, and does showcase some, though not that great here actually, the power of using these VGG features, or these deep learning kind of pre-trained features, just directly in your classification. Of course, if you want to be more disciplined, you actually might want to, you know, fine-tune the network a little bit. This is a common thing, to fine-tune the network after the fact to do better on this, but we're not going to worry about that because that's actually a pretty involved process. But of course, even in our case, what really matters is not just not this, right? Because we already did a lot better than this just using text. So what's the real advantage if we're going to use both? You know, this one, if it's doing already worse than we know we can do. So the real question, of course, is going to be how we do with images and text. Right? It's not just can the images do anything, it's can they do something that is you know, helpful to us above and beyond what we already see in the names. Now, there's a couple ways you can do this, and I'm going to take a very simplistic way in this, which is not necessarily the fanciest thing, but it will get at one of these, you know, it'll get at some of this. And that is just, we're going to now take our text features and our image features and put them all together. Right? So let's just take, instead of just doing text before, just doing images before, let's just put them together, and maybe we'll have this magical case where taken together these things sort of blow up and we get 100% performance, right? Let's see. Okay, so I'm going to take my original features that was somewhere up here. Where did I create them? Here it was. Yeah, question. Was there a question? Okay. So I'm going to take this, and also take my image features and put them all together. Now I'm going to also create a new training set and test set. And I'm going to go through this same process here of looking at the performance over a wide range of possible regularization parameters. This will take a few seconds. Any bets on what's going to happen? Who thinks it'll do better than both classifiers together, or originally? Who thinks it'll do just as good as the text one does? Who thinks it'll do no better than, worse than the text one? Who thinks it'll do worse than the image one too? Okay, let's see. All right, this is the one we have, right? Okay, so here's the performance. Well, it's exactly the same, essentially, as the image one. Just make sure I'm actually doing this correctly here. I have my features. Yeah, let's make sure we should have more features. Okay, yeah, we do. Okay, so why is this happening? Any guesses? Yeah. Well, so that might be part of it, but you know, the machine learning we're regularizing, right? So we should be able to sort of downweight the unimportant ones, right? Yeah.
No, we have just multiplied. multiply image by 0 and had a better performance. Like why it happens?
Yeah, so why does this happen? Any guesses? This is a really common thing you'll see. So I wanted to bring this up. Yeah. There's no decision, this is logistic regression here, no decision trees here. You can just set all the weights of the images to be 0, and that would do great. Okay, let me provide my take on why this is happening. So first of all, there are some things we could fix here, like the features are not perfectly normalized against each other. That's something we could fix. So we can try that, but you can do stuff things and it won't help you that much. So what's happening here essentially is that if you look at the performance that you get at that same regularization parameter with just text, basically at that level, and actually this would be fixed by these things. So you can fix this by regularizing better, but or by normalizing better. But and this is an important point, and this is sort of why I wanted to make this point. At this level of regularization, with the level that you've normalized the text features at, you basically get no dependence on the text features at all, right? It washes out. The image features are normalized differently than those ones, and so when you include those, you actually only trust the image features because they're just weighted bigger than the others, right? So that's why this is happening. Because this is a really common thing I see. When people throw features together, they don't normalize properly, and therefore they sort of make this mistake, and it seems like it isn't helping to have both the things when it actually might. So let's go ahead and fix that. Let's go ahead and fix, and we do this by essentially saying x train, or else look at the mean. X is equals 0. Okay, and now we're going to subtract off the mean from our training set and train on that. Equals x train minus x on the mean. That by x. I'm going to do the same for the cross-validation. Okay. Oops, what did I do here? Oh, right. You can't do that for all of them because some of them are I want to do this actually. You can fix this in more disciplined ways, but a common thing to actually do here is just add like 1e negative 10 here, because some features don't actually ever vary. So so the standard deviation is 0, so you're dividing by 0, so they blow up. Oops, not times, plus. I'll make it like 6, 7. All right, does everyone understand what was happening there? Essentially, the scaling of the two things was very different. What I'm doing now is I'm normalizing the scales such that they're all even. All right, so the scales are all even so that you have similar scaling. Now, this is actually not quite right thing to do because TF-IDF loses all its power, or it loses some of its power when you normalize like this, right? TF-IDF, the whole idea is you actually weight some columns bigger, and they use that. But let's not worry about that too much. Essentially, we're just going to be using term frequency then, not term frequency, or at least we're omitting the inverse document frequency, just kind of seeing if we can do this a little bit better. Okay, so now let's run this again and see how this works. Okay, what's going on here? Oh, I already did this. Hang on. All right. Okay. Who thinks what's going to happen now? Who thinks what's going to happen now? We're going to do better than the text now, than both of them individually? Better? Who thinks better than both? Who thinks no better than text? The power of text. Who thinks worse than text? Okay. Let's see.
Can you explain again why we had that?
Why we're having this? Yeah. So think of regularization. Regularization penalizes large weights on the coefficients. Okay? In order to make the weights meaningful, the weights themselves are only meaningful in combination with the features. So it's really the feature/weight combination that is meaningful. Now, I didn't show it here, but what's happened is that the features themselves of the images, they're fine amongst themselves, but they are larger weight, they have larger absolute values than the text features, right? What this means is that a small weight on those ones is giving you the same performance essentially as a very low weight on the other ones. As a small weight on one's giving you the same as a very large weight on the other ones. And so by the time you get to 0, you have C equal to 0, so lambda is equal to 0. You can get 100% performance on your training set by just looking at the image features. So it's going to do that effectively, right? It's going to put some weight on text too, but not very much. It's going to basically just be trusting the image features and ignoring the text. So it's very important. The punchline here is that when you combine features, it's very important to make sure they are on the same scale. Otherwise, especially with something like logistic regression, you are unfairly penalizing some over others. All right, let's see what happens here. So this is very interesting, right? So it's actually doing worse than all of these. So what's happening here is that we're actually getting the same effects, okay? Though we may think it's plausible, right, that you should be able to do better than both of them. What actually is happening is that with very little weight now, you can actually do reasonably well. You can do better than sort of anything that the images could do. And as you add more, you're basically just getting the range where you trust the image features still, and you're ignoring the text features. So there are better ways of doing this, but I want to highlight this because this is basically a big problem people run into when they try to combine features. Machine learning algorithms will not always do the right thing, or what you think of as the right thing, meaning trust the text features until you hit the point where you can't differentiate anymore, and then trust the image features. What's actually happening here is that by trying to combine all them, even after normalization, you end up doing worse than either. Well, I guess you're doing a little better with the images alone here, but with really low regularization. But you end up doing no better than you end up doing worse than your best classifier would do anyway. This, by the way, is one reason also why you still need to think about feature selection, modulo just what the learning algorithm does. You don't want to just always throw all the features at it and see how it performs. You will very often still overfit to your training set and still use features that are quite poor. It's a question there.
It's a heterogeneous model. That's what I like after the lecture. So why did we regularize in the last lecture? Normalize in the last lecture. If you do it without normalizing,
yeah.
we would have done better.
So actually you don't want to normalize the TF-IDF features, right? That was sort of the point I just made, is that it can work okay, but you actually don't want to normalize those. We're not using gradient boosting here, though. We're using logistic regression. So sorry, what was your question?
So if you don't normalize the features
Yeah.
and throw it to gradient boosting,
Yeah.
would it do better?
Yeah, so gradient boosting will do marginally better without normalization. And the reason is the decision trees don't require an absolute scale, right? They just use thresholds. Is it bigger than this and less than this? It's actually, they are to a certain extent invariant if you used it in the right way. They are invariant to rescalings of your features. Now, in our case, though, the classifier actually did worse than the logistic regression classifier. Remember that?
Normalize that.
We didn't normalize the first ones. We used a TF-IDF. So we didn't normalize when we had the text features alone. We just used TF-IDF, and that worked better in our case. Yeah?
So if you have like a lot of features, like 30 or 40,
Yeah.
would PCA make sense in any scenarios? How would
Okay, so the question is about whether or not I should apply PCA to this. It would do better. We can try. Actually, I don't know if it would do better here. Probably not. So PCA, and this is sort of an important point to make. PCA is an unsupervised learning algorithm, right? So it will reduce your number of features, but it does so in a way that only looks at the input data, right? So if you have some features that just by their nature have more variation than others, even if those features are irrelevant to the actual training set, it will happily pick those, or you put a high weight effectively on those ones to capture their variation, right? Because it needs to be able to capture that. On the other hand, if you have some features that don't vary that much, but which are very good predictors for the class, they have to vary a little bit, or they won't be good predictors. But if they vary a little bit, but are good predictors of the class, PCA won't necessarily pick those, or won't put a very high linear combination, won't weight those very heavily. So you want to be very careful about PCA as a way of sort of selecting what you think is the right features, because often it won't. Often it will pick things that vary a lot in terms of their actual, what they look like, but they're actually just meaningless when it comes to the actual performance. So we could play around a bit more with this, but I actually did on my own because I was hoping to show that you could actually benefit some from images, but I couldn't actually get them to help at all. The best I could do was get them to be the same by things like PCA and by things like feature selection. The best thing I could do was get them to perform the same by itself as a text classification. So this is an important point, right? No matter how much you would like, you see some effect here of images. It seems like, oh wow, we can use the images to improve things. I was not able to, in this case, get an improvement above anything more than a very marginal improvement, which I don't think, which didn't reflect on the test set, just on the cross-validation set, which is cheating, of course, right? You can't overfit to the cross-validation set. I was unable to get, by sort of standard methodology, or at least the things we covered in classifier, a classifier that improved performance on both these things over just the naive, just using text alone. And I think oftentimes people are sort of hesitant to accept this as a reality. They want these things to have an effect. But again, if you go back to the game we played, there were a lot of cases where I could just tell that what I was actually keying on was not the actual images. If you look at these two images, I knew this one was a better toy, right? If you look at the images themselves, rubber ducks are great, right? Maybe you like rubber ducks. But I know this is the Green Toys brand, and therefore I was pretty confident that this was going to be highly rated. I was myself internally keying much more on the keywords in the text than I was keying on the actual images themselves. And if you have both these things, if you can't get an improvement and you find yourself trusting one source of data more than another, this sort of gets back to our discussion on debugging data science. Don't, at some point stop and don't try to force it, because you probably won't. There's a good chance, at least I will say, that you won't be able to actually extract information from that great source that's there that you'd love to be able to extract information from, but just doesn't seem to be actually giving you any relevant information. So in this case, we're actually not going to dwell on that anymore, because I don't think, abandon things quickly too. So try out a lot of things and abandon them quickly if they don't seem to be working. In this case, it seemed promising initially, but didn't seem to actually improve performance. So let's not spend any more time on dealing with images. The one thing I'll say, which would be worth trying still, I actually didn't try this one, but I tried it a little bit, but not, maybe I could try it more. One key, if you want to do this, if you want to see can images add any marginal benefit to my existing classifier, is actually try to build a machine learning problem on that exact task. So essentially, what you do is you weight examples such that you have an equal weight of kind of incorrect and correct examples of your previous classifier, and you try then to see if an image-based system could do well kind of on this reweighted task. If you have a regression task, it's actually a little bit more clear what to do there. Essentially, rather than trying to predict the raw label with your new features, try to predict the residual of your existing classifier and see if you can actually predict well on the residual rather than sort of the raw input. So there are ways essentially to force the classifier to only make additional, to first trust entirely the text features and then only make decisions based upon the image features after that. But now you're getting pretty specialized in the pipeline, and I was not able to get that thing to work to get any notable improvement in test error, at least, over this. So try that by all means, but also be prepared to give up and be prepared to accept the fact that maybe despite your deep learning, these features just weren't actually having an effect on the task at hand. Okay, any questions there? Yeah.
So what's the intuition behind features that the VGG network generates?
Boy, so this is actually, so the question was, what's the intuition behind the VGG features? So this is actually a great question. And it's one that's it's very much a research question. How do you interpret the output of a large kind of opaque deep learning pipeline? So what people have done, the things people do with these is they look at certain outputs in the images, in the last layer of features, right? So these are essentially the activation of some long chain of neural network computations. They look to see what images have that particular feature have a high value or not, right? And by doing that, you can find that if you look in your whole training set, for example, on the actual ImageNet data set, this is what VGG was trained upon, you can find some examples to say, look, this neuron here is always active when I see a cat, right? And so this hidden unit here must be doing something about cat detection. For convolutional networks, you actually can do even a little bit more and say not just what was this, when's this on for, but where in the image was activating this particular output. And you can do essentially a visualization of saying, okay, if this one's high, here's the region of the image that was making it high across all my training set, and you can then see in the best case, oh look, it's all the cats that are making this neuron high. That is very much sort of an active area of research right now. And so unlike the text, where it's sort of very easy to look at, say, look, here's the weights on each of these terms. Bath is bad and toy is bad, but toys is good. Unlike that case, it's very difficult to sort of quickly give you a procedure for extracting understanding and meaning from the activations and the features of a deep network. It is a black box, right? It is basically saying, when I follow this long pipeline of convolutions and max pooling and nonlinear activations, I got this thing to be the values that they are. And saying what did that is very much still an active question of research. For text, for TF-IDF, it's a lot easier, right? You just say, what are my actual features? What are their weights? I can do that. If I tell you there's a high weight on this one activation in the deep network, it won't be that useful. Okay, so we're ready to give up and say, look, images don't really help, but we have this seemingly okay classifier based upon text. Let's just trust that. Let's see how well we do with that. So now comes sort of the final point of the pipeline, which is taking our system and actually deploying it on new examples to see what predictions it actually makes. So now let me do the following. Let me sort of go back to my original data here. Before I do this, I'm gonna actually rebuild my classifier based just upon the image. Actually, let's see, based just upon the TF-IDF features. I'm gonna build it here. I think it had 0.8. Sorry, I'm abusing my cells now, my notebook cells. Actually, no, I'm not going to do that. Sorry. I'm going to distribute this to people later, so let me actually do something a little bit better. So now, talk about deploying model. All right, so I'm going to recreate my features with ignoring images and sort of giving up on that, at least for now, until I can do more analysis and figure out exactly what I can learn by images. I'm just going back to the text images. But now I'm going to talk about deploying my model on examples where I don't know the actual rating. So remember, when I started off, my goal, I said, was that I want to find the toys that don't have many reviews that are still good, right? Because I want to get my daughter a good toy. It doesn't have many reviews yet because I don't want everyone to have the same toy. And in our pipeline, we filtered out all the examples that didn't have at least 4 reviews. In fact, when I first scraped, I only scraped things that had at least 1 review. I could actually probably go back now and scrape everything, including things that don't have any reviews. But I'm going to go and I'm going to say, let's just do the opposite. Let's look at all those ones that have less than 4 reviews. Ignore what the actual reviews were, because there just isn't enough data to give us a good sample yet, and see if I can find amongst those that aren't reviewed very much yet, which are the best toys. Okay, so I'm going to rebuild my model here, making sure that I'm getting something reasonably accurate. I think it was 0.8, the resolution we used for the previous one. Okay, that looked good. And now I'm going to reload the data again and follow a different pipeline. And in fact, I don't think I saved it around, so I'm just going to copy this code again. Let's see. Okay, this. And I'll call something else. I love my naming convention here, very intuitive, of course, df0 equals pd data frame all items. I want to filter some of the things the same as I did before. So I believe I filtered things with the number. Where was this? I filtered it by looking only at the things that had price. No, this is before, after I had the Bayes rating. Let's see. So first I have to do this one. So I'm going to now I'm reloading my data here, so I'm just repeating this. You probably should have saved my original data frame before I threw out the ones that had less than 4 ratings. And I'm going to call this, so this should be ZF0. All right, so now finally I'm going to now keep only the ones with less than 4 ratings. And I'm still going to drop the ones without price because I'm using price as a feature. So I have to be able to use price. So I'm going to say something like df0 equals df0, num ratings is less than or equal to 4. So I want to keep only these. I'm also going to copy it. Sometimes when you take a slice of a data frame, it like takes the original. It doesn't throw out the original data frame, and you get weird things. So I'm going to ignore that. And I'm going to drop a subset equals price. All right, so hopefully that all was correct there. OK, so now I have a different data set. It has only my items that had fewer than 4 ratings. And I want to take my classifier now and apply it to this case. So I'm going to create features first from my new guys. So let's say xdeploy equals stack. I think tf-idf was the name of my, sorry, tf.transform. Name dot, let's see, this to array. OK, so what I'm doing here is I'm creating a new, remember, I have now my data frame, which is my data frame of elements that are rated all less than 4 times. So they all have 4 or fewer ratings. They have everything is the same as that. Now I need to transform it to be in the same set of features as I had before, right? So the way I do that is I apply the same transformations that I did before. Importantly, they have to be done in the same order, right? They have to use the actual same transformation objects. So I had this tf-idf object, which is what I use, what I use to build my tf-idf in scikit-learn. That's up here. Let's see, it goes way, way up. Where was my tf-idf? It's right here, right? Yeah, so I used a tf-idf vectorizer, applied it to all my things before to get things. Importantly, I have to use that same set of features. I can't create a new tf-idf vectorizer and apply it to my new training set because there's going to be different words in that, right? So it's you have to use their same, when you're deploying a classifier, you have to use all the same feature transformations you used when you built the classifier, not the ones that you sort of the same pipeline you would apply to your new data. So this is a point I really want to, does everyone understand what I mean there? I could have create a new tf-idf vectorizer object and applied it to my data. That would have given, of course, completely incongruent results. So a different number of features, different everything, right? You wouldn't have been allowed to apply my old classifier to that thing. So to apply my classifier to new data, I have to use that same set of features. And then I also have this price value. So I'm just going to go ahead and use that. All right, df0.price. Let's see if this works. OK, what's going on? Transform to array. OK. And let's make sure it's the same shape as my other one. So that's the same shape, same size, features, everything looks the same. Well, it's the same because I built it to be the same, but everything is in fact the same here. All right, and let's get a score by looking at the decision function of our classifier. So we trained our classifier above. It can predict what are good toys and what are bad toys. So now let's set df0. Let's make it have a score function, and this is going to be the decision function applied to xdeploy. Again, for these ones, I don't actually have. It's actually the negative decision function if I want positive to be, because remember the labels were inverted. So I'm going to just keep it simple, do that. And this now attaches to each of them a predicted score from my classifier. So let's look at this again. Now it has a score. This is a score ranging from negative infinity to positive infinity, where high means it's likely a good toy, low means it's likely a bad toy. All right, so now we're done. Now we've applied our classifier to new data. The last thing to do is to see what this actually looks like. By equals score. And we want to look at the good ones first. OK, so any guesses on what this is going to look like? Let's look at the top 20. Any guesses what this will be? This is now, I've taken my my data. I've looked at only those examples that have fewer than a certain number of reviews, and I've applied my classifier to this to get a score for each of them. So what's going to be at the top of this list here?
The branded toys.
What is it going to be?
The toys that are good brands.
Yeah. So let's see. So let's actually just look at the names of the toys, because we were using based upon the names. So basically, it's a whole bunch of brand name toys that don't yet have 4 reviews. So most brand name toys actually have more than 4 reviews. They're popular toys. They have a lot of reviews. We've built a classifier to differentiate between that, found that they were, in fact, a good signal for getting things, doing things well. So what this data is telling us is not really that revolutionary, right? It says what you should do if you want to get a good toy that no one knows about is find a good brand and then find a toy that doesn't have very many ratings yet that is of that brand. So I believe all the top ones are Melissa and Doug, Fisher-Price, or this Brio. And that's the good toys. What are going to be the really bad toys? What are the bad toys going to be? Yeah, bath toys. They have the word bath and toy and water. This is like the worst possible toy, right? It has water and bath and toy. We can see what his actually ratings are. I mean, these aren't going to have many ratings, but actually, the worst one actually just happens to be rated a 2, the 1 rating, which is not that common in Amazon. So there is some generalization here where the bad toys, bath toys really do seem to be bad. Of course, there's also some good ones here. This one's a good one despite being a bath toy, but there are some bad ones too. So that's all the analysis I have. So that completes our little walkthrough. And I do want to emphasize this last point is that don't necessarily expect anything kind of transformative from your data science analysis. Oftentimes, what it will tell you is not something sort of you couldn't have guessed yourself, but it will tell you what's in the data, right? So what is in the actual Amazon data, if you just use that data, is the fact that name brands tend to have, certain name brands at least, tend to be rated higher than other brands. So if you train a classifier on it, that's what's going to happen. You're going to extract that information, and you're going to build a classifier that knows that. You're not going to have some amazing classifier that says, okay, this toy, somehow it'll know that the kids love this one in a way that's not, they just can't be captured by the data that's actually there. So see what you use to actually make the classifications, and then if you're hoping for a classifier to do something more than that, you're probably going to be out of luck. So that's sort of going to conclude this analysis. Any questions now before we move on to talking about data science jobs?
Do you have any intuition why bad toys or physical toys?
Yeah. So again, this is now from my parent standpoint about why I think this is bad. Bath toys in general sort of, kids don't like baths, right? Kids don't like taking baths. And so the hope in the parents when they buy a bath toy is that they'll buy this toy and all of a sudden their kid will love taking a bath. That is not usually the case. Putting a toy in the bath does not make your kid want to take a bath. And so I think it's a psychological thing where other toys are only good. Kids love the other toys because they're just good things. Bath toys are all things you give to the kid in a possibly negative environment. So of course people aren't going to like them as much. Again, that's a complete conjecture. This is my conjecture. When I was the first time, it's like, oh yeah, maybe that's why. I would guess is that because bath toys are something you give a kid when they're unhappy, whereas other toys are something you give them to be happy, right? And so that's my guess. But I said that's completely like psychological, which is actually interesting. But this is an interesting feature of this data that revealed something that the top ones I could kind of guess. The fact that bath toys are all awful, I would not have guessed. And so it forced me to come up with some conjecture as to why this might be the case. Now, whether or not it sounds good, right? I have no idea that's true or not, but it sounds good. And if you wanted to investigate that, you should probably go to some of the bath toys and see why they're rated negatively. I don't know for sure, but my guess is going to be some people say, my kid hated this toy because they already are in the bath and they're already unhappy. But we'll see.
Do you find your score for words like bath is really less? Is that also?
Yeah. So the TF-IDF, the raw score, So TF-IDF is just going to mark how many are in the document, or how many in the document, which is usually 1, which is that's term frequency. IDF means the inverse document frequency. So that's going to be kind of a middling, maybe not a huge factor actually. You take the log of it, so it's not going to be that huge. So it really is much more the actual classifier weight assigned to that feature rather than the raw TF-IDF score. Yeah, because the TF-IDF couldn't ever know that it's a negative word. It just can weight it by a certain amount based upon the frequency it occurs. It wouldn't know it's correlated negatively with its class. Yeah.
So we got some interesting results which said that toy was acceptable, but toy wasn't. It's possible that we as humans might try to read into that, but it may not really.
Yeah, exactly. That's a good point too. The fact that toys had a high weight and toy had a low weight probably is meaningless. It probably is an artifact of the data that just happened to be the case that maybe there were a lot of bath toy, right? Bath toy is a common phrase, so maybe that's just all it was. If you want to try to figure out if there is anything more substantial there, you should go back to your data and see which are the ones that have toys versus which ones that have toy, and try to differentiate somehow. I suspect you're right. I suspect that is a meaningless distinction. That is just an artifact of this data set. Yeah. Yeah.
Sir, I wanted to do the weighting thing that I wanted to weight more the text,
Yeah.
not the features of the
Yep.
How do I actually do that?
Yeah. So the question: how would you go about actually weighting the text more? The simple way to do it would be to bump up the magnitude of the text features higher than the magnitude of the image features, because that, for logistic regression, would make the classifier more likely to pick those things versus the others. So you could actually have another sort of regularizer that just sort of also had a fixed weight on the new image features and varied that between, the full weight, which we know gives bad performance, with 0 weight, which we know gives good performance, right? That would be another way of doing it. I haven't run that. That actually would be interesting to run and see if there's any point. I don't think there is, but is there any point where you get a little bump in the performance over just the pure text features? Okay, so about halfway done now. Maybe we'll get through the next lecture, maybe not, but we can talk. The lecture on Wednesday is going to be kind of open-ended, so we can certainly finish some of the things on data science jobs if we don't get through all this now. Okay, so let's see. All right, so there are no more questions about the practical walkthrough of data science, which gave us this amazing insight that you should not get bath toys for your kid and get them name brand toys. Let's switch gears now. Let's talk about data scientists. So by far, actually, this is the most common question I got in my lunch meeting so far was, how do I get a job as a data scientist? I mean, not in so many words, but basically, how do I get a job as a data scientist? So I want to take some time to talk about data scientists and what data scientist means. And I'm going to talk a little bit about data science and industry. The majority is going to be focused on industry here because I think this is still largely an industry term, an industry position. When you do it in academics, you're just doing research in some other field. You're not necessarily doing data science. But in industry, there's definitely this position called data scientist. So what is this position, and how do you go about getting a job as a data scientist? I forgot the announcements. I should probably make this at the beginning of class. Okay, switching gears again. As you probably all know, we issued an extension of 2 days for both the final, the homework 6, and the report. The one tonight, you can use late dates if you have them. You cannot use late dates for your final report. That is due. Hard deadline is the midnight on the 11th. We have a room and time now for the video presentations. It's going to be 5 to 8 p.m. In Rashid Auditorium on the 14th. Attendance is mandatory. I actually changed this a little bit, but now I'm going to let you know. I'll make a post on this. But my current stance is now is that attendance for this is mandatory for everyone. This is both 688 people watching it on video and people here in class, 388. So it's mandatory unless you get exception from me. So we will take attendance there, and it is mandatory unless you get acceptance, unless you get an explicit note saying for me it is okay to not attend. I will post more about this today on Piazza. Videos are going to be submitted by midnight on 12/13, so the day before you have to submit your videos. They're 2 minutes long. There will be a harsh limit, and you can see in the actual video. The problem with doing live presentations is that 2 minutes is very short, and people will always go over. So we have a hard deadline here, so that's why we're having videos, actually. I'll have a little more information on sort of what you can do as a video also, what I might suggest, though you're also free to do whatever you want. You can be as fancy as you want with your videos. And you're going to end up posting a video to YouTube. You'll post it yourself, and just send us the link to the video. It can be unlisted, so you don't have to make it public. You could make it public if you want, but it can be unlisted. And you'll just send us the link. We don't want to deal with getting like large MP4 files that we can't play and stuff like that. So send us the link on YouTube by this time. And that will be also, again, a hard deadline. You have to send it to us by then. More on that today. And there will also be pizza for the session. Maybe we'll try to get some vegetarian or vegan options as well, so that not everyone can eat something. But you'll get to have dinner during this time. Okay, so let's talk about data science and industry. Before I start, though, who here has applied for a data science position of some kind? 1, 2, 3. Well, let's say 1, 2, 3, 4. It's gonna be a really bad sense of the thing, but it seems like it's about maybe half the class that's applied for data science position. Who has already done a data science internship here? 1, 2, 3, 4, 5. Maybe a fourth of the class. Who here has worked as a full-time data scientist at some point? All right, no one yet. Good. Maybe, I don't know. It doesn't matter. and I guess then who here is interested in the vaguest sense in applying for some sort of data science position at some point in their lives, if they have not already? Not that much more, actually, than the half that already have. So you've already selected yourselves out pretty well. What was that? Well, no one changed their mind after taking this class, because they've already, well, I guess they could have applied during the class and then done it, but no one changed their mind. Okay, so I mean, and I hold, I think part of the appeal of this class, certainly, I knew this going in, right, is that hopefully it was appealing to those that wanted to apply for data science positions, to have some notion of what you want to do next, or some idea about what it might actually involve to be a data scientist. And despite this fact, though, I think, and even after taking this course, I bet the most common question I will get still is, what is a data science position like in industry? What is actually involved? And the reality is there's not a great answer to this, because the name data scientist is still a position that is not well defined. It's probably actually not unlike software engineer in that sense, that software engineers become to mean this sort of incredibly broad thing, but it's probably even more broad than that, right? Because software engineer, at least it means you're probably gonna be writing code. When you're a data scientist, you could be doing really anything. And so because of this, I kind of want to, this is not an exhaustive list, but I want to highlight the fact that there really are many different types of data science positions. And so just jumping into a couple of these kind of, there's no real order to this list, is that some positions of data scientists are really just business analysts, right? They were just, 5 years ago, they would have been called a business analyst position. That name got less trendy, and so now they're called data scientists, but it's the exact same job as before. Business analysts it's not like anyone didn't look at data when making the decisions, right? Maybe some did. Maybe you had some pure pundits hired in industry. But for the most part, people are using some data. It's just that these ones tend to be much smaller amounts of data. They do things like work with Excel sheets and play fancy tricks with Excel to do their analysis. But that still is a position that's now called data scientists sometimes. The same is true for statisticians, by the way. A lot of jobs which are formerly just statisticians, so these are things where you actually, you create samples, you basically do hypothesis testing, significance testing. This now very often is advertised as a data science position. So this used to be called a statistician. That term is now not as sexy as data scientist. So people use data scientists now, but it's just a statistician job. You're doing the same thing. You're using R probably. You're tabulating results. You're conducting surveys maybe, and that can be very just like statistician also span the whole range from very sort of creating surveys to doing research. These data science positions also vary for the whole spectrum of creating surveys to doing research. There's also a notion of kind of like a product manager that's a little bit more of a data scientist now. So you're fill the role more of a product manager. In other words, you're kind of developing products. You're kind of seeking out what products to make, but you're doing it from a more data-driven perspective. There are machine learning engineering positions where your basic goal is to take models that have been developed by statisticians or by yourself and then code them up so that they are a part of the main platform that your product is releasing, that your group is releasing, or that you somehow are developing as an engineer. Man. And then finally, there's kind of a more tools developer. So there will be positions where you're actually developing tools for other data scientists. You're writing libraries that either internally the company or externally you can use to do other data science work. This is by no means an exhaustive list, so I don't want to highlight the fact that it could be an exhaustive list. I just want to highlight some of these things. But really what I want to get to is some kind of important distinctions to look at when you think about data science positions that I think are more important than kind of the name of the job, because these are the things that actually affect mostly, in my experience, what you will do day to day. So one of the biggest distinctions that you will see in data science positions is the following. Is your company that you are working at, are they developing products where data science from the beginning is an integral element of that product, right? Are they kind of trying to do develop AI style products, or not everyone uses the term AI now, but really it's really just, are they using data science to develop products from the get-go? Versus, are they a company that already has a product out there, right? That's already working fine as a product, and your job is to be brought in and just to analyze their data and see what value there is there. And this is a very important distinction, and I've seen very different roles at companies based upon which class of data scientist you're going to be. So if you're in the first category, you are going to spend much more time developing products and developing tools that will actually find their way into a released product. Just by definition, they are building their products based upon some amount of data science. And so you are going to need to do some sort of product development, an actual understanding of, can we actually craft what I'm doing here into a product? If you're in the second one, then you are much more kind of on your own. You are much more sort of saying, okay, we're going to be fine without you, for lack of a better phrase. But if you can tell us something really cool about our data, we'll be really excited about it, right? And so you kind of sit on your own, kind of in a room in the back, maybe. You don't really operate that much or integrate that much with the company from day to day. But you get all their data. You look at it. You kind of think to yourself, are there any interesting problems here? And then you say, if there are, you can do something that sounds very, changes the way they sell some product or changes the way they do some analysis. Both of these, importantly, have very distinct advantages and failure modes. So the advantage of the first one is, if you succeed, you're going to have probably a much better chance of having your things deployed, on a large scale. The failure mode, though, is that sort of when I first talked about debunking data science, remember one thing I told you is that there are lots of problems people would love to be able to solve, but which actually do not have any signal in the data. And you will encounter a lot of these if you are a product developer, right? Product development will not focus only on what is possible through data science. It will focus on what product managers and bosses would like to produce. Okay, so if you have this, and clients, by the way, too. So if you are in this first category, chances are, and I kind of put actually data science consulting in this first category too, because often you talk with a client and try to figure out, can we develop a product that you guys want to buy? But there, kind of data science may be at least a core part of that relationship. Now. There are often going to be times where a client or a boss would love to develop some product. They read about machine learning, and so they want to develop some product. And you do some quick analysis, and you just can't actually do it, right? It doesn't actually work. This is going to be the failure mode of the first kind. That's going to be, you have a very hard time convincing people something's actually impossible, or that they shouldn't be looking at this. And if you do that, you probably should actually you're going to have to come up with some alternative when something is impossible. You'll have to propose some alternative of what they could build instead of the thing they wanted to build in the first place, because it's just not, they want to break the stock market. They can't do it. And so you have to tell them, sorry, I'm not going to make you $1 million a day. I'm going to do something else instead. That's not going to make you nearly as much money, but trust me, it's really a good idea. The failure mode of the second type is sort of the opposite. I mean, if you're not going to be typically as sort of, if you're not going to be as ensconced in impossible problems, because you will have a chance to actually do the analysis and beforehand and determine what is and is not possible before you actually go ahead and propose this as a product. But the failure mode there is sort of the opposite. It's that because your company is operating kind of fine without you, there's a good chance that everything you do will be ignored. Unless you have a really, really compelling case for why what you're doing is going to be simple and add substantially to the existing business value. Because if you're working for some company that has an existing product which is profitable, you better have a really good case about why you can make it better before they're going to trust things to your hands. So I've seen these two things a lot, and they both kind of have their benefits and their downsides. And if people are curious, I'm actually curious. Actually, out of a quick survey here, of the people that did data science internships or data science positions here, who felt they were more like the first type? Wow, no, one person. Two people, maybe? Not sure yet? Oh, no, who already have done one? Still not sure, okay. Maybe, I mean, this is a spectrum, right? So it could be kind of in the middle. It's possible too. Who felt like they were more in the second type? The second one's a little bit more common, I'll say, in positions, because it's easy for a company to do that, right? It's easy for them to hire a team and just say, here's the data, do cool stuff, and not really care if you do something or not. But the first one is, has its benefits and drawbacks as well. I said something before, actually, and I might rethink that. The role of kind of a data science consultant, which is not a position I'm really talking about here, because I'm talking more about working for a company that wants to do data analysis themselves. But the role of a data science consultant can actually be either of these as well. Sometimes you will approach a company and be able to, if you work for a larger organization, they will have already set up a relationship, a consulting agreement with some company. Your job will be to just look at their data, see what you can do. Other times, data science will sort of craft the original engagement with the new company, in which case it's going to be much more of the first type. So in the data science consulting world, there actually are both types here that happen. The next big distinction is that I see is that between developing tools for the data scientists or for the company as a whole, and actually doing the data analysis yourself. So there are data scientists whose main goal is actually not to do any data analysis to speak. Their main goal is actually to write tools for the company as a whole, or maybe even if you're really lucky, be able to open source them for the world as a whole, to be able to do better data scientists. These are often very highly sought after. People like the idea of sort of building machine learning tools because it seems like they're going to have a big impact. You could have a big impact if you do the sort of the tooling work. There's a potential for a very big impact, but oftentimes there's a very high bar to clear before your company's API or your company's toolkit they're developing will be used either internally or externally above existing tools. It's a very high threshold to cross before you can be better than Pandas. Even though, as everyone knows here, Pandas is awful. I shouldn't say that. I really like Pandas, actually. But there are some hiccups with Pandas. But I've gotten a lot of complaints about Pandas. Just trust me, you will have to do a lot before you can clear a bar such that people want to use your tool instead of Pandas. Because Pandas is actually quite nice. I shouldn't say this on video. I was being tongue-in-cheek when I said it. But I like Pandas. That's why we use it. So this is sort of, I mean, this should be very clear when you take a position, which type you're doing. The first two usually matter a little bit less. Or sorry, they don't matter less. They are less clear oftentimes in the job description because people don't differentiate them as much. The second one, companies tend to differentiate between those two. So they will let you know in your position which it is. And the third type, the third distinction rather, is between positions that are going to emphasize classical statistics versus sort of newfangled machine learning. And again, the point I hopefully made in this class was that as far as the vast majority of what we do is concerned, there really isn't that big of a distinction between these two things, right? They're both minimizing a lot. I mean, I use the word machine learning algorithm, but you just easily talk about a statistical algorithm as the same thing, right? You just use, the log probability as your loss function instead of, something you made up in an ad hoc manner. But I do think this is an important distinction because what this actually means is the tools people are going to want you to use can vary between being fine with using linear regression to solve your problem versus people seeing that and saying, well, this is not what I'm paying you for. I'm not paying you to run linear regression. I could have hired anyone to do that. Your job is to apply deep learning to these things and see what that will tell you about my data, right? So this is a tricky thing to sort of get a handle on. I think this is also not widely advertised, other than maybe in the keywords that the job might say that you need to be familiar with. But there will be a distinction between companies that want to be using deep learning for its own sake almost more than anything, right? They just want to be able to say they're doing deep learning work versus companies that want more to have a statistical analysis of their data, regardless of what type they actually care about. And oftentimes classical, so-called classical methods end up being the best here, right? So be aware of that too. That is oftentimes more, a decision that comes from what the company wants out of a data science position. Do they want kind of to be seeing what they can do with latest and greatest machine learning, or do they want to really understand their data? So that's the distinction that people have. Has anyone here, by the way, experienced, I'm going to let people talk a little bit because I'm running out of voice here. Has anyone experienced any of these trade-offs in their positions? What was your experience of any of these?
So on the first point, I said I was confused because initially they wanted me to just analyze the data,
Yep.
but eventually that would have become a product.
Okay. So that's a good way of doing things, actually, if they really want to do that. If they really want to analyze data first and then develop a product, that's great. Oftentimes, I've seen that they typically actually have a product in mind before doing any analysis, and they want to analyze it so that they hopefully can come up with the answer that they already had beforehand. Yeah.
I had a similar problem, but not the exact same, wherein the company was kind of, so we used feature selection to narrow down on some of the features that we needed to use.
Uh-huh.
But they were of the opinion that to improve accuracy and throw in a lot more, so they just wanted us to add in a lot more, even though contextually it didn't make much sense.
Yeah, I've actually experienced the same exact thing before, where you go to a client and you say, we have a classifier where we've taken your whole set of features and reduced it to 10 to give us good performance. And they'll say, well, why are we paying you for just using 10 features? We want you to use 1,000 features. And it doesn't matter the accuracy, right? They want this notion of using lots of data. So, so feature selection, you just come up with an automated feature selection method, and then say that you're using all the features, but just you happen to discover that the weight is 0 for many of them. So you're still using 1,000 features, 15, 10 million features, right? And you're just only using actually 10 of those to actually make your decision. But you're still using them all. It's just they have a weight of 0. So by the way, this is actually I'm saying this somewhat jokingly, but as a data scientist, there is a lot, I think, as we sort of all know, of preconceptions about what people think they want out of machine learning and out of data science. And part of your goal as a data scientist, frankly, will be education. Educating people in terms of what they actually want versus what they think they want. This will be a non-trivial part of your job. And understanding how to convince people that they really do just want 10 features is actually a very non-trivial and important part of being a data scientist. Someone else is there. Yes?
Another thing which I realized over time is this distinction between data engineering and data science.
Yeah.
That's one of the things
Yeah, so that's a great question about the distinction between data engineers and data scientists. Data engineers are more kind of the tool builders, right? They are or alternatively the ones working with the real data science team to take the real data science team's output and just code it up in Java instead of in Python, because you don't want any Python in your production application. Hopefully, that's going to be less and less of a thing as more companies develop better pipelines to deploying models. But yes, there's a big distinction between kind of a data engineering job, as it's defined, which is usually much more classical software engineering that somehow relates with some results of data science, versus data science where you're doing a lot of the analysis yourself, or at least ideally doing some analysis yourself. Yeah.
engineering and data science is that data engineers are augmenting the work that machine learning, engineers are doing. So they are like creating stabilized data pipelines.
Uh-huh.
By, doing it in a large scale, and mostly in ETL.
Right. Yeah. So my opinion on this, frankly, is that this still varies by the positions. There's no sort of set rules here. Some data engineers are more like machine learning engineers. They're sort of writing some of the machine learning algorithms. Some are more like, thinking about data processing pipelines. Some are thinking more about just sort of what the output of a data science team is so they can code that up in their platform. Just like data scientists, there's no good definition yet of data engineers, and so this will vary from position to position. But yes, in general, when a position has engineering attached to it, chances are you're going to be writing more code in the platform where your main deployment, your main product is, and chances are you'll be doing less kind of open-ended data analysis if your position title has engineer in it. Yeah.
Two questions. One question is, especially with regards to the machine learning part, do people usually in industry always code their own machine learning algorithms, or they just usually tend to use whatever is available, like scikit-learn?
Yeah. So the question was, do people in industry tend to use their own tools or what's available? My impression is that by far the majority use existing tools. There aren't many shops that even will write simple algorithms because you don't often need to. There often are. It's perfectly good to use existing ones. Even for things that are really simple, like I kept stressing that gradient descent for an SVM is 5 lines of code, right? But it's still 5 lines of code that could have a bug in it. So why bother using that when you know that there's some package out there that has no bugs in it? So the majority of places will use libraries, not write their own routines. If you're in that tooling section, you may be in the exception. You may be the exception to this, but probably you will be using existing tools that are out there. However, my point that I kept emphasizing is that to use these tools effectively, we are still at a point where you have to understand what they are doing behind the scenes, right? Because otherwise they are very opaque black boxes that you will just not actually understand and not know how to tune to actually improve their performance when you want to debug them. So by all means, use a package. I used packages here. For this, I didn't write, even though when I was doing really simple algorithms here, I was not writing it myself. I was using scikit-learn. You'll probably do the same, but you want to understand what's going on behind the scenes. Yeah, second question, right?
Yeah, and my second question was, so when I saw a lot, so this happened a lot, like people used to go to a lot of these companies at the career fair and say that, we are interested in data science and machine learning solutions. And a lot of them just said, okay, we're only accepting PhD.
Yeah, I have actually a slide on that exact thing in a few slides. Yeah, so let me actually address that in a second. I'll get to this part, probably the academic section, which I'll leave till next time, including actually, by the way, independent study opportunities. I'll leave that till next lecture, but I'll finish up this portion here. So this is my advice for applying for a data science position, and this is my own advice. Your mileage may vary on this, but the first thing I would do internally is try to get as many clues as you can from the position listing about what type of job it actually is. And by the way, if people are applying to data science jobs, I'm happy to give any sort of advice on particular ones to a limit. If I get inundated with requests here, I might have to triage some. But if you're curious, by all means, let me know. I'm happy to chat with you about it. But my sort of recommendation here would be first, try to figure out what they actually want when they say data scientist, because they may not even know what they want. And that's probably a good reason not to go there if they don't know what they want. Though who knows, maybe you can really influence things that way. Identify what you think you're going to be doing. Are you going to be largely sitting in a back room working on their data or developing a product? Are you going to be writing tools versus doing the data analysis yourself? Once you've done this in your application, do absolutely highlight your relevant coursework. Do mention you've taken this course or machine learning or anything else you've taken. But also, probably even more importantly, highlight some independent applications you've done as well. That could include, by the way, the course project, but you probably want more than just that to have a really good chance. You need something a little bit more than just that. The reality is, it is understood in a lot of companies doing data science that just doing coursework here is usually not sufficient to be an expert in data science. You gain expertise by experience in the area. So they're going to want to see some evidence that you've been able to do this kind of analysis in a, in a less rigorously defined setting in the classroom environment. So if you have GitHub pages, if you have blog posts, anything you've made relevant to data science, by all means include those in your application. That's going to be actually quite important. And then finally, this is something that this is something that people might disagree with me on this, but mention the tools you know specific to the opportunity that is actually there. So, and tailor it to the actual requirements, to what they actually want to use. So if you're going to a place where they use R, do not talk about how great you are at Python. I mean, you can mention it, but highlight the fact that you know R. We don't use R at all here, but if the company I worked for, we use Python primarily. And when we see people that highlighted only R and never mentioned Python, that was hard. I mean, maybe they would be fine, they could pick it up, but you have to mention the tools. Look at the tools they're asking for in the application, and give examples of things you've actually done that use those tools. It does not take very long to learn a tool. So often, I mean, honestly, if you are really gung-ho about a position, take the time to learn the tool. Have a GitHub page where you use the tool. It's just take you a couple days, right? And highlight it that way, because even if that's irrelevant to the actual position, it will be a filter that they use to say who they're going to give an interview to and who they're not going to give an interview to. So those are sort of quick things of advice. Maybe they're not that helpful, but I do think that these are the things that sort of end up helping people get positions. And the last thing I'll talk. Well, not the last thing. I have a few more things. I have something about interviews next, I guess. Shoot, we'll see if I get through it all. The last thing is to your point as well. So there are a lot of positions that sort of say for data scientists, minimum of a PhD and 5 years experience required. And the reality is that really is a bogus requirement for all but a very, very small number of positions. What they are trying to do when they put that is they are trying to reduce the variance in their applicants. They are trying to, they don't know what they want, probably, more than anything. And they also know these are a set of skills that is, frankly, in high demand. It's not very common yet. And so they are trying to find a smaller pool of people where the variance within that pool is going to be lower, right? That's all they're trying to do when they say PhD required. Chances are your job does not need a PhD. Even machine learning engineers don't need PhDs. They can just learn the algorithms, do the work, and you'll probably be fine. Unless you are genuinely doing kind of cutting edge research that really needs this fundamental understanding, you can get by fine without a PhD in most practical positions. I've very rarely seen things we need PhDs for when I worked in data science, when I worked in industry. So these are not actual requirements of the position. And if you can get your foot in the door, you will still have a good shot. But you will not be able to get your foot in the door easily. So don't give up just because someone says that. But if you go to a career fair, they're going to tell you that. They're going to say, no, we're not looking for that right now. We're looking for software engineers. That's only for PhDs, right? If you know someone at the company, if you have any connections there, try to exploit those connections, because chances are the jobs don't require that. And once they actually interview you and see that you know the things, you will be an asset to that team. But they are saying that to reduce their variance. So you probably won't be able to. I mean, chances are, in any given case, you won't be able to skip the line. You won't get around. But if you can, you will probably still be suited to the actual position itself. If you know, for example, I think that mastery of skills that were taught in this course, if you have that, that is sufficient for most data science positions in industry. All right. Oh man, I really wanted to cover this today. I don't think we'll have time. We don't have time at all. Just sort of a few things, because I don't know if I want to cover this next time. For people that have interviewed in data science positions, what were you asked in your interview? What topics were you asked about?
I wasn't really interviewed. They sent me a data set.
Okay, yeah. So this is like a data analysis project. What was you at too? What were you asked?
I was asked to, so I had
asked about machine learning
Uh-huh.
having to explain a particular algorithm
Yep.
and talk about things like overfitting and
Right. Yep.
the other one was a statistics kind of thing where they wanted to know certain specific concepts that
Great. Great. So okay. I'm doing well here on the next slide. You asked probability questions? Okay. Anyone else? Yeah.
One of my interviews, they actually gave me a laptop and made me code in pandas.
Okay. Yeah. It's like like a take-home thing, but a live thing. Yeah. Yeah. Anyone else? What questions were you asked? Give me like 2 more minutes. I don't want to leave this tailing for the next time, so we'll go through it. Yeah. Okay. Okay, so like machine learning algorithms, how they work and things like that. So I find there's again no standard here, but these are the type of questions you're going to get in general. So the first thing you can get is you will probably get some standard software engineering questions, just write an algorithm that solves this sorting task, right? If you need to use a stack to do it or whatever. You get questions. You sometimes get asked questions about data processing, so like questions about SQL and things like this. I've seen those in people's interviews, and then I think the rest I got right here from what people said, right? So those two you will see. Maybe people weren't even answering those. I bet someone's got some of those as well. But you will see machine learning questions, and like I said, they're oftentimes more about training and testing and performance like that than concrete stuff. But you will be asked about actual machine learning algorithms too. So hopefully, the stuff you learn in this course, you learned here, will actually be useful for the interview as well as in practice. And then you'll be asked about stats questions. So you'll be asked about hypothesis testing and probability and sort of classical statistics in terms of this whole field of knowledge. And then finally, I think this is actually very common in virtually any interview you'll have for data science, is you'll be asked, because they don't know what to ask actually, because they have no clue what to ask to test your actual knowledge of data science, they'll give you an analysis project to do. That could either be a take-home one where you write it, or it could be an in-person one where they want you to do it on the fly right there. But those are probably the most common things I'll see in almost any data science interview. So when you're applying for these jobs, do know that they will probably have one like this. They will probably ask you a bunch of knowledge that I think is largely covered in this course. In fact, part of the impetus for this course was when I was interviewing potential candidates, I wanted them to know everything that was in this course. That's sort of why not why, but that was part of the motivation for some of these topics. But be prepared for these things when you're interviewing for data science. All right, next time we're going to have our final lecture. It's going to be largely open-ended. I'm going to post some Q&A topics on Piazza, so you can actually ask questions about what you might want me to talk about. And I'll also, lastly, talk about the second half of this lecture, which was going to be about opportunities to do more data science research and things like independent study here at CMU in the remainder of your time here. So we'll address that also on next class. Okay.